Okay. All right. Welcome to the last session, I guess. So this is a review session. I'm just gonna go over last year's final exam. I would say this year's exam you'll expect something very similar, at least in difficulty and length. So. So let's. Any questions before we start? General questions?
Should we worry about like the adaptive control stuff we talked about in the exam at all?
Short answer is no.
Okay.
We covered very little on that. I don't. I mean, I would look at it. I mean, you're allowed to bring all your notes, right? So, but I don't think I haven't seen the exam.
He said he wouldn't test us on anything that wasn't like sort of covered on the homework.
Yeah. So there's a very good chance that stuff won't be on the test. And like the last two lectures, I think. It'll probably cover up to the input-output feedback linearization. So, all right. So somebody had the exam. So number one, it says, so you're given a nonlinear system and it's a describing function question. So your system looks like this. So this is a cubic nonlinearity, and you're given the describing functions for them. So this is the IDF assumption. So part A asks, if k is 1, prove that the limit cycle is unstable. Okay. So we have some sort of limit cycle here. And this is a classic Nichols plot question, right? So what you need to do is plot the Nichols plot of this, L, this N, right? The Nichols plot of L and the Nichols plot of 1 over N, right? And then see if they intersect. So to start, you might want to have a Bode plot, and just really roughly it looks something like that, where that's -1 slope and 3 slope, and you've got it's a function of 1. And your associated phase goes from -90 degrees down to the 70, and it looks something like that. Okay. So this should come very easily to you. So make sure study your Bode plots. So we have the Nichols diagram. And our L on the Nichols diagram just goes from our magnitude, so like the magnitude is increasing that way. So it goes something like that. Right, as omega increases. And now we have a look at our n. So somebody tell me which n we're going to use. NA. Because here we're just looking at the limit cycle. It's a high frequency sinusoidal, if you will. Right? So we look at NA. So 1 over NA is just 1 over 4 over 3. So as we increase A, so 1 over NA decreases, right? And when A is very small, this is very large. So we start from like way up here, and then we kind of and the phase, because it's negative 1 over NA, right? So I'm just gonna, so the magnitude is that, the phase of this. Is negative 180, right? Because of the negative sign. So we're gonna go down the minus 180 line. So you see that they intersect here. So that's a limit cycle. But is it, we want to show that it's unstable, right? So for that, we need to do a Nyquist, right? So this question is very involved. For the Nyquist, it looks, so we're drawing the Nyquist of L, and that basically when we have, when omega is 0 or DC, we approach from negative 90 degrees and a large magnitude, so we're coming up like this. And then as omega approaches infinity, we end up at negative 270 degrees, so up here, and we have a magnitude of 0, so it's like one of these. Right. And so it comes like up like this. We draw the other one, it's like that. Which way does it go when it goes to infinity? So here you could just kind of tell by inspection there's only one pole at the origin, so that it's going to go this way. But you can verify it to yourself if you do. Just draw out the poles on the real imaginary plane, and then just kind of work your way around this pole that's at the origin, right? So over here we're at negative 90 degrees, so that's positive 90 degrees, that's up here. And then when we get to here, we're at 0, so that's over here, and then we're back at negative 90. So, right, pretty standard stuff. So now we have the Nyquist plot of this guy, and this guy just comes in like this from the minus 180 degrees. And you can see that when you increase A, there you go in here, and there's 2 encirclements, right? So 1 and 2. So if you recall the Nyquist stability criterion, you get n is 2, so we have 2 unstable poles. So we can conclude that based on this, that the limit cycle is unstable. Any questions on that? Let's do this. So part B says find a K of S that will yield a stable limit cycle with a frequency of approximately 100 radians per second. So, how do we do this one? Well, to have a stable limit cycle, what we want is for our Nichols diagram. So we have this, right? So if we could make this L or KL do something like this, okay? Then this point right here is going to give you a stable limit cycle. How do we know for sure? Well, if we draw the Nyquist diagram of something like that, we have it's coming in like this and it's going back like that. Okay. So if you did the whole thing, right, you'll find that here you get two encirclements here. So there's one encirclement in the other direction and one, so they cancel out. And then over here you get two. So within this region right here, it's stable. Okay. So what we want is this intersection right here to occur at a frequency of 100 radians per second. Is this clear? So what kind of K can we make? Actually, I'm going to draw the Bode plot back again. So here we have -1 slope, -3 slope. This is at a magnitude of 1. And this is -90, -180. What we really want is for this crossover to occur at omega is 100 and our phase at -180 degrees, right? So, so this looks like, so we got something here, goes down like this. We want this to come back, right? Come back to 90. And at this point, we want this to be 100. So how does this happen? What can we do here to make that happen?
Need more than one.
Yeah, more than one. Yeah. So if you did something like K and some K naught times S plus 100 squared, okay, that's gonna, over here, this is gonna get you back to -90 degrees, right? This will get you back to -90 degrees, and it will give you a crossover at approximately 100 radians, right? So that means from here, if we add that, now we're back to a -1 slope. Are we done? Why not?
because you want ST for drop off.
Exactly. Right. So for our describing function to be valid, we need, this slope down here to drop off really quickly, right? To filter out the high frequency stuff, the harmonics. So what can we do? Well, one thing we could do is we could try to, somewhere over here, to bring the slope back to, let's say, a -3 slope, right? At some higher frequency. So what will that do? That's gonna make this go back to the way it was, right? And then our Nichols plot will look like that. So you can pick some high value. I chose 1,000. Okay. So he made your K something like that, right? Then that would work. You see the logic behind this? So I think that is part B. So part C asks to, with your K that you chose, what is the transfer function from YC to Y for low frequency inputs? Okay. So this.
Just a quick question about where you added the S plus 100.
Yeah.
Is that because you have two of them? So like at 100 you have about 45 degrees of phase, and because before it was at about 270. So then if you add 45 twice, you get 90, which brings it 180.
So each one of these gives you an extra 90 degrees of phase, right?
Well, but isn't that only like an extra 90 degrees after pass?
Right. Yeah. So at the crossover point, yes,
It's 45.
it gives you 45.
Okay.
So you add those. Yes, that gives you 90. So your crossover is at 1.
Okay. Alright.
Hey, Rick,
Yeah.
Is there any way of knowing that like your roll off of -1 isn't good enough? Like I mean, I understand like you need a bunch of roll off, but like how do you know if you have enough roll off or not? Is there any way to tell other than like simulating it or something?
I think in class we kind of intuitively said whenever we have only a roll off one, it's not
Okay.
it's not so good.
Okay.
About 2.
Definitely you want 2 or more.
Okay.
That's kind of a rule of thumb. You can verify if you simulate it, obviously. You could also kind of do a quick numerical example to see how much roll off you would actually get if you have 1 or 2. Okay. So we want Y over YC for low frequency. So we could write the transfer function. I'm going to call this. Right, so that's just the transfer function for that. Do I use NA or NB?
NB.
For low frequency, yes. Use NB. So NB is 3 over 2 times A squared. What is A? See, A is this input. That the magnitude that enters the nonlinearity. We don't know what A is. Okay, so we have to find A somehow. So how can we find A? So recall that the ID-IDF assumption allows us to use to basically design everything using this A, which is for the sinusoidal input, and then use the same A for the low frequency, right? So to find A, we actually have to go back and look at the limit cycle again. And how do we do that? Well, we could, we write out the condition for the limit cycle, or neutral stability, right? We have this, so that means L, the magnitude of L, that's the magnitude of NA is 1. We know that our L, actually, sorry, KL, because now we've added the K. Right. So, KL times 3 over 4, A squared is 1, and A squared is 4 over 3 divided by KL at our limit cycle frequency. So omega equals to 100. So to find A, all we have to do now is to find this magnitude. So we could say KL is what we had before. Times 1 over S plus 1 squared at. So here's where Professor Rock says doesn't need exact numbers here, so you can approximate your transfer functions. So for instance, when S, so you sub in J omega over here, and you get, this is approximately 2 times 100 squared, and this 1000 is much greater than 100, so you get 1000 squared. Over here you get, so 100 is much greater than 1, so you get 100 squared, another 100, so 100 cubed. And so this should be approximately. So you end up with something that looks like that. Okay. So from that we can get A squared to be 2/3 10 to the 8 over K0. So now we just sub this into here. So we can find K and B times L, and that's going to give us K0 times S plus 100 squared over S plus 1000 squared times 3 over 2 A squared, which is 2 over 3 10 to the 8 over K0 times 1 over S plus squared. Okay? So you see that it doesn't matter what K0 is, they just cancel out. So you end up with, so actually I'm not even gonna write it down. Anyway, your final answer is just 10 to 8 times S plus 100 squared over S plus 1 plus something like that. So any questions on number 1? pretty long.
Could you explain again how, like, why we use the A from, like, limit cycle?
Right. So when we're making the IDIDF assumption, we have a y coming in, right? So this is gonna be, so this is some like low frequency, slowly varying signal, and we're gonna have some A, A cos omega t plus b. And our A is, so this is our kind of, if you will, like dither frequency or something, like you could think of it that way. It's basically the frequency of the limit cycle, and that we determined, right? We found that from the previous part. So we said we wanted our limit cycle frequency to be 100. So the nice thing about this assumption is, when we're making this assumption, now everything only depends, so the describing function only depends on A and does not depend on this B anymore. So the A is from our limit cycle. So when we have the low frequency inputs, we still have our limit cycle going really, really fast, right? And that's why we need to figure out what this A is. I don't think I'm making this out very clear.
So we know that it goes to omega equals 100 because that's the state of the limit cycle.
Yeah, so that's what we designed for, right?
So we can assume that that's the limit cycle the system will go towards, and metal will go towards that limit cycle.
Yeah, it's a stable limit cycle. So, I mean, here's just, well, we're only solving for a limit cycle here, right? With this analysis. So, and when you show that this is stable, then you can use that as the limit cycle for the system. Okay. Number 2. Phase plane question. So you're giving so you're given this system, and the equation for this is x double dot minus x dot is u, or x double dot is x dot plus u. So the first part asks you to sketch the phase portrait. So let's just jump right into it. You can break this up as x dot dx dot dx. Move it to the other side. You get x dot plus u over x dot. So now you gotta kind of be creative, and you can do some method of isoclines, or there's some key things you can get from this. So one of the key things is if x dot is really big compared to u, because u is plus or minus 1, right? So if x dot is really big, then this is just 1. right? So, oh, that's about a switching line. So that's just x dot of x 0. So if we're way out here, or way down here, right? Then we could say our, we just have slope of 1. Also, this slope is 0 when x dot is negative u, right? So over here in this region we got u is negative 1, we got u is plus 1. So in this region when x dot is plus 1, then the slope is 0, right? So I could say this is 1, and we have 0 slope there. Similarly, we have 0 slope here. Okay. Could do a few others, like let's say x dot is 0.5. What do you get? Well, I'm going to write this as 1. So plus minus, yeah. So if u is negative 1 and x dot is say 0.5, then you have negative 1 over, so that's 2, so negative 2, so 1 minus negative 2, you got negative 1 slope. So on this line you got something that looks like this. On this line you got something that looks like this. All in all, you end up with trajectories that look like this. Here. It goes up like that. And then over here it comes over like that. And then down here it goes like that. So that's your phase portion. Over what region of the face plane is the system controllable? So meaning you can drive x and x dot to the origin. So it says you don't need equations, just careful sketches. So this just mainly comes from symmetry, right? If you say, look at this region right here, we have a trajectory that comes and then meets this point, and then over here we got trajectory that's here. You can show that this whole region in here is controllable, because basically what happens when you have a trajectory in here? Let's take this one, right? So it gets to here, and now we switch to one of the other contours, right? So this is gonna go like this, right? And you can see it's gonna go in the other. If we're outside here, if we're right here, this is just gonna diverge, right? Part C, can chatter occur? Along what portion of the switching line? Be specific. What do you think?
Yeah.
Yeah. But where does it occur?
When the slope is greater than -1, or more negative than -1.
Yeah. So what we're looking at is when this slope is -1, right? And I'm gonna do this. So I'll write it like this. This is a minus plus. Here's -1. So that means we've got 2x dot minus plus u is 0. So u is just 1, so x dot is plus minus 1/2. And what's happening here is these trajectories, this one comes here, and now it's got a switch, and there's one of these trajectories that are just precisely tangent. Right? So that's going to push it down, and then it's going to come back up, and then it's going to shatter all the way down to the origin. So similarly with this side. So basically we have shatter when x dot is between negative 1/2 and 1/2.
Just a question about that,
Yeah.
like, it seemed like in the other examples, like, when we reach a chatter zone, like, both were pointing downward, whereas in here, like, if you look on the left side, isn't it pointing up, so wouldn't it, like, get stuck in that region? Like, on the left side of the line, isn't that trajectory,
Oh, I see. So
It's a
yeah,
shallower
so
slope.
yeah, so it's hard to tell on the face on here, but you would basically have a steeper slope and then like a shallower thing,
Okay.
and then a steeper thing.
okay.
But it's hard to draw. Might have to take my word for it.
So for the one that you're saying is tangent, that's from the u
Yeah.
equals -1 side.
Yes.
It's like just when it hits.
Yes, exactly. Yeah. So it comes over here, it switches, then it gets pushed back. Any other questions on number 2? It's a pretty long exam. Okay, number 3. So we have a system. X double dot plus x dot plus x minus x cubed is 0. And we have some diagonal function. Like that. So when you're given a plot of the contours of V, that kind of looks like this, and then I guess it kind of branches off. Something like that. So in what region of the state space is V positive definite? So here we're given a contour plot of V, so we can sort of use that. If we knew one point where V is 0, then we can just kind of trace that along the contour and see where it's positive. So we know that when at the origin V is 0, right? And if you go, this is x, this is x dot. If you go along this side, along like the x-axis, then let's say x dot is 0, right? So when x dot is 0, we have V is half x squared minus quarter x to the fourth. It's going to give us this. So we can see that when this is positive, then V is positive definite, and this is just along this line, right? So this happens when magnitude of x is less than root 2. And what this looks like on here is if you count the rings on the plot, you'll see that it's never mind, that it's one of these. So you could say that within this region, so within this region, V is positive definite. Second part says in what region is V dot negative definite, negative semi-definite. So V dot. So this is pretty straightforward. We just take the derivatives. Times double dot plus x minus cubed. Okay, but this is kind of like the equation we have. So we have x double dot plus x minus x cubed is actually negative x dot. So this whole thing negative x dot squared, which is negative semi-definite.
So the region is the whole state space.
Yep. But the interesting part is part C, where it asks, in what region of the state space can you claim asymptotic stability? Well, this one is a little bit tricky, and the best way to approach this is with the invariant set theorem. So if you say, so this is negative semi-definite because anywhere along the line V dot is 0, x dot is 0, so the x-axis, our V dot is 0, right? So when x dot is 0, V dot is 0. So we could say I forget what the denotations were, but I think this is our R, and then within the R we want to choose the largest invariant set M, right? And you could show that M is just the origin, because if you say that is 0, then the only way for x double dot to be 0 is when x is 0. Or when they're over here, right? That's it.
It's one and negative.
Yeah. Oh yeah. So here. So there's 3. This is so yeah. So we got 1, -1, and 0. And these are like saddle points, right?
Is R an invariant set or only M?
So
This is the invariant set.
R is the region where V dot is 0,
Okay.
and M is the largest invariant set inside that R. Okay, and so the invariant set theorem says you know, within this region, right? Within some region, right? All of your trajectories are going to M essentially. So we've shown that M is either one of these or all of these 3 points, right? And you could show that these two are unstable, sorry. Because if you kind of take a cut, right, across this and draw out B, it looks, you know, something like that. Right. So this is V and this is X. So here's our origin, and here's -1 and +1. So how can we show that these are unstable? Well, you could
First method.
you could use the first method of Lyapunov. Something else you could do is, remember the invariant set theorem says V is bounded by some L, right? So if we choose this L such that that L is this contour that's the biggest closed contour, right? That's kind of that goes from -1 to 1, but not including these points. Then you could show that within this region, all the trajectories must go to the origin. So, moral of the story is, the region that you can claim asymptotic stability is this kind of oval that's between -1 and 1.
Rick, so I never understood why we can't just say the invariant point with the lowest potential is our stable.
So in this case, that's exactly what it is.
Right.
Yeah, because this is essentially like a total energy, right? But in other cases, your V might look different. So I think it's a little bit restricting, especially if you have higher order systems. For second order, it's always easy to see, right? And yes, you could say that. But when you get to more complicated systems, then you kind of have to follow the theorems further, or else it's kind of hard to see.
How did you know that's how D looks against X?
So you're given these contours, and I'm not sure if during the exam they were color, but on the PDF it's color.
You can evaluate it, right? Because you know the points.
Yeah, you can evaluate it, but you're given the contour, so you know that V is increasing and then it's decreasing down here.
How would you evaluate it? I mean, it's a function of both X and X dot, but then you're just drawing it as a function of X.
Yeah, so this is kind of a cross section when X dot is 0.
Oh, okay.
Yeah.
Okay. So on the exam it was color, so we would have been able to tell.
I don't remember if it was color. It could very well have been black and white.
So, a question on, like, is the reason we can't, because we found that V dot was positive definite in that larger region, like on the bottom, that hyperbola looking thing.
Yeah. V is
is-
positive.
Yeah, so at the end, we can only conclude asymptotic stability in that region.
In this region, yeah.
Is that because it's not radially unbounded?
So it's kind of a
If it starts
It's-
at either of those arrow points, it's not going to leave.
it's a limitation of the theorem, if you will, because if you start it here, it may very well come to the origin.
This also right
However, using this theorem, we can't.
Well, but why is that? Because we found that I guess I'm
Because the-
3 points, like our invariant set is 3 different points.
right. But if we use linearization, we found that 2 of them were unstable, then it would have to go to the other one, right?
Well, unless it starts at either
Yeah,
of those 2 points.
within this region.
Yeah.
Within this region, because if you're outside this region, your v might go negative. Right? And definitely over here it drops off, so you're gonna diverge if you start anywhere. That's outside there. But there is definitely a region where trajectories will converge, but we can't show that they will converge. And that's kind of the limitation of the Lyapunov analysis. So if you found another V that works in this region, and you can show that, then you can add that to your region of convergence. That's kind of how this game is played. Okay. Okay. Cool. Number 4. So your system is x dot, x1 dot is x2, x2 dot is negative x1 cubed times x1. Use the first method of Lyapunov to prove the origin is unstable. That's easy. So your A just F1 dx2 dx2 dx1 2 dx2 evaluated at x is 0. So what do we get? Yeah. 0, 1, 2, that's great, plus 1. So we get 0, 1, 1, 0. We take the eigenvalues of that matrix. So determinant of Si minus A gives us, so S minus 1, which gives us S squared minus 1. Which is unstable. Part B, show that the set of points defined by its function here is an invariant set. So we have this function that's x2 squared minus x1 squared plus half x1 to the 4 equals 1. How do we show this? Any ideas? No. So essentially we're gonna make some sort of Lyapunov-like function, and let's call this take the whole thing, square it. and then take the derivative. So we're gonna get I'm looking for a shortcut. It's not. Actually. Sorry, never mind. Yeah, to show that it's an invariant set, we just have to take the derivative of this, right? Getting ahead of myself. So we can define some function f of x equals to this. So we can do f dot is 2x2 dot minus 2x1 dot plus 2x1 cubed x1 dot, and sub stuff in. So 2x2 is negative x1 minus 2x1 times x2 plus 2x1 cubed times x2. So do you see how this cancels with that and this cancels with that? So it's 0. So it's an invariant set. Part C is the set of points defined here a stable limit cycle. Now we define the V. So now we can define our V to be f squared. And then we can take its derivative, which is f squared f dot. Okay. So what do we see here? So we just showed that f dot is 0, right, along any trajectory. So that means, so this guy is 0, so that means v dot is 0 for all the trajectories. So is this a stable limit cycle? Why not?
Because if you had a point off the, aren't these just like conservative orders, so like they don't stay on themselves?
Yeah. So so v dot is always 0. So these are just kind of they don't converge to any single trajectory. All the trajectories, all of the contours of v are trajectories of the system. So they just kind of keep circling around. So I actually plotted this, and it looks something like this. There's these two things here. So it looks like that. So no, it's not even a limit cycle. That was the trick in that question.
How do you show that mathematically? How do you show that mathematically?
You didn't have to do this. You just say that since v dot is always 0. Remember, for us to converge to a limit cycle, your v dot has to be at least negative in parts of your region, right?
How is it that you can't say, like, maybe if I had found a different v, it might have been negative?
So the question asks, is the set of points defined here? So they want, is like, are these points a limit cycle? Right, so when we're defining our v, it's I'm not really sure what else you would define it, because we define it basically as the distance that we're off of this. Yeah, I haven't really thought about other v's.
But in general, if you define, if you pick up like the